Third lecture on magnetism. Just within a short time, I will try to cover the Langevin's theory of diamagnetism. Actually, the whole process may take 1 hour for the complete explanation and derivation, but as it is an online class, we will brief it because some problems in uploading and downloading processes. So to avoid that, let me complete this in brief. You already understood what is magnetization and susceptibility, etc. So by considering the basic equation again, B is equal to mu h or B is equal to mu naught h, and the susceptibility is magnetization per unit volume of for the applied field. So by remembering this, let us work for a dipole. So this is Langevin's theory of diamagnetism. So what is important here? As you know, the diamagnetic materials are not having their original field unless you apply a magnetic field orthogonal to the particular direction of the movement of the electron. So the original magnetic field is already absent in the diamagnetic material, and it is always influenced by the magnetic field. So here, according to Langevin's theory, we have to solve both the conditions. In the absence of the magnetic field, what happens? And actually, in the presence of the magnetic field, what happens? So we can consider a dipole momentum, or the same what I considered in the last class, loop of the current given by the movement of an electron. So electron will move here. So with a particular radius vector, it is having an angular velocity omega everything. So here, what are the forces you come across? Usual force is centripetal force for this particular electron. It may be mv square upon r. So this may be centripetal force. When the electron moves with the frequency d nu or nu, you know that omega is equal to 2 phi or omega is equal to v by r. You also know that the particular frequency nu is nothing but omega divided by 2 phi, or the change in the frequency delta nu, or it can be written like this, maybe d omega by 2 phi or like this. So you have to remember these expressions. So after remembering all these things, let us solve the particular theory in two different steps. What is the first step? In the absence of the magnetic field, first step itself, in the absence of the applied field. So there is no applied magnetic field. So then how do you take? This particular F is nothing but, or this is nothing but F is equal to F naught minus Fl, where F, this is actually m omega square r must be equal to this particular force. I can take as mv square upon r here, okay, minus Fl is Eb omega into r. So this is nothing but the by applying the Lorentz force is always given by, Lorentz force is nothing but E into B cross V for a particular radius. If I take, this is E into B into omega into R into R. Omega is okay. So this is nothing but B into V itself. Okay. So therefore EB R omega, if I take like this, because this is E into B into omega R. Either you can take only this much or you can express like this. Now by taking this particular fundamental equation, either we can solve for any one of the quantities here. So it comes in the form of a quadratic equation, so that you can find the particular root of this particular function. So let me take this equation freshly again. Okay. So in the absence of the field, we can work out and find the root of this particular function. After that, we can go to the next stage when the field is applied. So I will keep the diagram in the same way. Suppose I can take the total force here as, again, F is equal to F naught minus Fl, okay, where F is equal to mv square of r, or this F is equal to mv square upon r, or you can also take nothing but this is f naught, f is equal to m omega square r, and your Lorentz force is E into V into omega, or E into V into V, or this is nothing but omega into r. So this equation is the first equation. Also you can take the quantity f naught, that is mv square upon r, may be taken for the nucleus of an electron, but this is nothing but usual centripetal force. This is one quantity in the equation 1. So what about this particular quantity f? F is m omega square r, that can be taken for a nucleus like this, that is square upon 4 pi epsilon naught r square. So this is a usual quantity what you can take for the particular force f. You can solve this back. This is m omega square r may be equal to z square upon 4 phi epsilon naught or epsilon into r square. So if I solve for the omega square here, this is omega square is equal to z square divided by 4 phi m r cube. This is z square upon 4 phi m r cube. So this value is required for us in equation 1 to solve, because you know the value of f, it is solved here. You know the value of f naught, and also you know the value of Lorentz force. So Lorentz force is already observed on the electron. Now by having all these values, we can substitute these values in equation 1, and you can get a particular quantity, as I told, to solve the square root of an equation. It will just substitute very simply, as this is m into omega square r itself must be equal to same quantity what I have taken, z square upon 4 phi m epsilon naught r cube minus this is E r omega b or E b r omega. Okay, E r omega b. So by taking all these particular quantities here, simply now let us have this as equation 2. You have to solve this equation 2 to get the value of the frequency. Also the particular change in the value of the frequency can be estimated. So just divide this equation by m into r. So you can get m omega square r by m r must be equal to z square 4 phi m epsilon naught r cube into 1 upon, this is only 4 phi, okay, epsilon naught r cube. So this is 4 phi epsilon naught mr, okay, this is actually mr square minus er omega b divided by mr. Okay, so here rr gets cancelled, this becomes r cube 4 pi, and here also we can only have the omega square must be equal to z e square 4 pi epsilon naught m into r cube minus e into omega into b upon m. Okay, so we can have this particular form, e into omega into b upon m, or this particular quantity and the whole equation we can call it as equation 3. Now you can solve for the root. Okay, so after solving the particular root, you can also have this particular equation. You transform the quantity of whatever you want like this. You can also write omega square plus e omega b upon m must be equal to, or you can take minus z square upon 4 pi epsilon naught mr cube must be equal to 0. Now Equation 4 is an exactly a quadratic equation with the particular roots. You have to find the roots of omega. It may be plus or minus b into b square or square root of b square minus 4ac upon 2a. So in that form you have to get the root. So I will directly write the root of the equation 4. Then I solve further. By taking the square root, you can have the particular root of the equation. Either usually it is w is equal to minus eb upon m plus or minus under the square root symbol eb upon m whole square minus this is plus 4 omega naught square divided by 2a, that is 2 into 1 is 2. So here we find therefore omega may be taken as either plus or minus square root of this is nothing but omega naught square plus eb upon 2m whole square, okay, minus eb upon 2m. So here I can get a condition whether the frequency is nothing but eb upon 2m, okay, here that is nothing but the frequency related to the angular velocity, or the quantity itself is an angular frequency. So therefore, suppose you can say for the quantity eb upon 2m may be very lesser than the quantity omega naught. So in such cases, straightway you can write omega may be plus or minus of omega naught minus eb upon 2m. So this is very important expression what we can derive and name it as equation 5. Now depending upon this quantity, we can either operate the quantities like eb upon 2m wherever we require. It is all the process which is happening in the absence of the magnetic field. Now what happens? This is for the first stage. This all happening in the usual absence of the magnetic field. But for the Langevin's theory, let us examine how the particular electron in the loop will behave after applying the magnetic field. It perfectly behaves as a dipole, so that it possesses the dipole momentum, and when it possesses the dipole momentum, the change in the frequency can be taken. While there is a change in the frequency, change in the current is also taken into account. So therefore, what is the value of the total current derived after applying the field? Let us examine that. So the second condition in the Langevin's theory, in the presence of the magnetic field. So what happens actually? Magnetic polarization takes place so that the net dipole magnetic momentum is observed. But two important cases will take place here. Most of the electron magnetic dipoles which are following the particular path along the loop while they constitute the current, actually in the absence of the field, the total current or the net value of the current is 0, because the movement of the dipoles or the electrons which constitute the current is the particular moment which produces the total magnetic momentum is 0. Net magnetic momentum is 0. So therefore, the value of the current is also 0. Because you know that the dipole momentum mu I may be nothing but I into A, where I into phi r square. I is nothing but E into the frequency mu into phi r square. This E may be the charge, where this is nothing but omega upon 2 phi. So into phi r square. So by this analogy we can take the particular quantity. Okay, so let us work out this. But before going to work out this, in the presence of the magnetic field, some dipoles do the exact magnetic polarization. It is comparable to the dielectric polarization. So the particular electrons taking part in the magnetic polarization will sum up their magnetic momentum so that the current is also increases. So they are all nothing but properly oriented magnetic dipoles after applying the field. This is the main theme of the theory of diamagnetism. So according to Langevin, some properly oriented dipoles under the influence of the magnetic field constitute the net dipole magnetic momentum. So that net dipole magnetic momentum may be calculated. But there are some magnetic dipoles which are antiparallel again, some. So they will not constitute the exact current. So we can take for the net dipole magnetic momentum constituted by these particular magnetic dipoles when a proper field is applied. So this is the very important aspect in the Langevin's theory. So therefore, let us say, so what is the total current here? Let the total current for the number of electrons in the nucleus, because we have considered the nucleus, the electrons are moving, may be having a charge, for that the total current may be nothing but this particular Q into frequency F. So here we can take Q as E, F as nu, isn't it? And therefore I is nothing but E into nu. But usually, what is this particular E? This E here is Z times of E for n number of dipoles. Okay, in the nucleus. So therefore, I can also take this is nothing but I is equal to ZE into nu. Okay. So this is a very important equation. What I can take on the basis of this. That equation has some 5 in the first case in the absence of the magnetic field. Here is the presence of the magnetic field. Before going to calculate the net dipole magnetic momentum, we can take like this, and here this equation we have to operate further. So what is the nu here? Nu is nothing but actually the frequency. Okay, and that frequency nu actually is omega upon 2 phi. Okay, so what is omega? Omega is already derived. Omega is derived in this is nothing but EB upon 2m. So this is derived according to the theory of the current constituted by an electron in a loop, either in the absence of the magnetic field or in the presence of the magnetic field. Same theory. It actually explains the Larmor theory, and the value of this frequency is the Larmor frequency. Anyway, so omega is what? EB upon 2m. So I can call this has 3, this has 4 in this. Or actually if I want to continue, this is 7, this is 8, equation number 8, and this is equation 9. So therefore, nu is equal to EB upon 2m into 1 upon 2 phi, that is EB upon 4 phi. This is the value of the frequency in the presence of the magnetic field. This